Hello, this is team number one, and this is our video presentation about experimental methods.
My part was water quality and hypothesis testing. What did we do? We measured the pH, the TDS, and the conductivity in each floor of Aulas 1. So we went to the fountain where we take water and we took samples with a digital TDS meter and a digital pH meter and digital conductivity meter. So it was a tool that we fill that cup with the water of the fountain of the drinking fountain of each floor. We measure it, we clean it, and we did it again. So what was our hypothesis? Or what was the hypothesis? The null hypothesis, it was that fountain water comes from the same source of the tap water. The alternative hypothesis was fountain water comes from a different source, possibly filtered, and I use C-test to compare the mean of pH, TDS, and conductivity. And we use the C-test. The sample data, these are the sample data. I'm not going to explain each one of either one, but what we can see is that conductivity it's quite big, high, sorry. So yeah, we took the mean of each one and we made the C. So the significant difference in TDS and conductivity was 2.08 and 2.84. pH was not so significantly bigger. So we suggest that possibly the filtration or treatment was only on the first floor. So in our conclusion, most fountains are chemically similar to tap water. Only the first floor fountain showed statistically the significant differences. Differences might be due to filtration, the pipe age, or maintenance, so it can be a lot of factors. It can also affect the device that we use to meter all this stuff. So we have to do that again in another time so we can see a difference of the data that we could change and it can vary. Thanks.
Static spring measurements. In the part of measurements in this experiment, we measure how far a spring stretches depending on the weight applied to it. First, we measure the length of the spring without any weight, and then we added weight and measure the length of the spring each time. The weights were 0.2, 0.35, 0.5, and 0.7 kilograms. Force versus extension graph. To create the graph, we first calculated the force exerted by each weight, with a formula of force which is equal to mass multiplied by gravity. And with these values, we plot the graph of force on the y-axis versus extension on the x-axis.
Now let's go with the linear regression and the spring constant. To find the relationship between the applied force and the extension of the spring, according to Hooke's law, the slope of the line in the graph represents the spring constant k. So from the regression analysis, we got the next values. F is equal to 71.721 plus 0.1452. So K is equal to 71.721. Now, according to our results, the spring has a spring constant of 71.721 newtons per meter, which shows a relationship between force and extension that confirms the Hooke's law. Although there was a small positive intercept, the relationship in the regression line shows an approximately linear trend, and the model provides reliable within the experimental range.
The third and final experiment was the oscillation spring experiment, which basically consists of 5 different masses that we as a team decided to obtain the average period. In this case, we use different masses like 1 kilogram, 1.2, 1.5, 1.6, and 1.7. Then we proceeded to slightly displace the mass to then track the movement in the y-axis and obtain the different graphs you see at the right of the screen. Then we proceeded to measure the period, which is a time difference between each spike, and then we average it to get an average period for each mass. Then we linearize the equation. After obtaining the period, we have that the equation was t equals 2 pi times the square root of the mass times the k constant. So we first squared each side of the equations, and then it transforms to a straight line. So the slope is equal to 4 pi squared divided by k, and if we solve for k, it ends up at k equals 4 times pi squared times a, where a is represented by the slope uh, obtained from the graph of the masses times the period squared.
And then we finally get the k value from the slope itself. Shortly after, the values of the mass and the period square were plotted and were fitted against the best line, where the intercept value is 0, to obtain the slope that represents the value of A itself. In this case, the value was 7.3813 kilograms per second squared, and if the value is multiplied by 4 pi squared, the K constant can be obtained, and we got 291.4 newtons per meter.